So the last topic here is MCMC diagnostics, and going through this will help us understand earlier in the JAX code. Remember, like we have to do like sample as well as mean and also number of chains, all that. So those are things that you're able to choose. And now let's go through the basics of MCMC diagnostics to see why we care about certain aspects of running an MCMC algorithm. And Gibbs sampler is a typical tool. It's is one type of MCMC. Okay. All right. So the thing is, remember, the goal that we have is we want to get the distribution of all of the parameters, the posterior distribution of the parameter. The thing is, once you have more than one parameter in the model, it will get very complicated to look at the joint posterior. So we came to what we talked about, the full conditional posterior distribution, that we're able to sample each of them sequentially, okay, iteratively. But at the end of the day, we're hoping that the draws that we're going to get, say, for example, in the normal case, we're hoping that the draws that we get from the Gibbs sampler, so we get like a large number of draws of mu, right? And also, I guess, a large number of draws of sigma. And those draws are coming from the Gibbs sampler. And we know how they did, right? Like mu given the previous sigma, and now the new sigma given the current mu, all that. But at the end of the day, we're hoping that the Gibbs sampler, the draws that we have, will be able to converge to the target or the actual joint posterior distribution. So that's what we're hoping to do. So one thing at least that we noticed, I think two things at least. One thing is, last time I think Josh was asking, well, does it matter where we start the chain? Does it matter where the starting values are? So if you imagine that if our Gibbs sampler, the draws are converging to the actual final posterior distribution, then the starting value shouldn't matter, right? It doesn't matter where I start. I should come eventually to the parameter space. So that is one reason soon you will see that we're going to chop off a lot of the draws at the beginning, because we don't want them to affect the convergence of our chain. Another thing I think last time I talked about is Monte Carlo. When we covered it before, we're doing independent draws, right? The independent draws, there will be a good summary of the actual posterior distribution. But when we're doing Gibbs sampler, which is MCMC, which is Markov chain Monte Carlo, and the Markov chain aspect of it is how we're doing it iteratively, in a sense that, say, remember, mu s is being drawn from this normal, let me use a different notation, is being drawn from this full conditional posterior distribution of mu given the data as well as the previous draw of sigma, right? And then we come to the point that we're doing sigma or phi, I'm just using sigma for now, that we're drawing it from y, so sigma given y, and the new draw that we have of this mu. Okay? So you can see that because of the iterative nature of this, the draws that we're going to get are not independent. Okay? There's going to be some dependence among them. So another key things that we're going to do after we get a long run of the Gibbs sampler is to make the draws from dependent to independent. The ways to do that is we're going to check a function to see the correlation between the draws. And say if the correlation is 10, for example, like I wouldn't say 10, sorry, is high, then because correlation is going to be between -1 to +1. And if it's going to be high, then we're going to like only save every 10th draw, or every 20th draw, or every 50th draw. Okay, so that's what we're going to see. The thing function earlier in the JAX code will be able to help us doing that. Okay, so those are some stuff good to keep in mind when we go through this part of the lecture. So the goal is that our MCMC, the Gibbs sampler, should converge to the posterior distribution, and we need to make sure that that is happening. So we're going to cover a few diagnostics to make sure that this is happening. And if it's not, we have to figure out a way to make sure that it is really converging. So this is the goal. So these are the few questions for you. I already talked about some of them. Do the initial value matters? Should they really matter? Markov chain indicate dependence of draws, how to create independent parameter draws. And another question, how long do we need to run the MCMC to adequately explore the posterior distribution? And how can we tell if the chain is not converging? So those are some questions to keep in mind. Before we move on, since I talked about especially the first two, just check with the neighbor like quickly to see if you think about, like, how do you think about the four questions here? Like, say, in your mind, what can we do to make sure that we're able to have a convergence of our Gibbs sampler? Open-ended, of course. Okay, anybody wants to make any comments to any of these four questions? Anyone? Yes.
We talked about for the fourth question, you could graph the values that you're drawing and visually assess whether they seem to be getting closer together.
Yeah, so graphical tools will be something we're going to use pretty extensively when we're doing diagnostics checking. Okay, so soon you're going to see, I think, trace plot is one way. And also later for part 2 over here, to look at the dependency between draws, we're going to create or like return the values of autocorrelation function, and then that can help us.
Is that really helpful though? Because we don't actually know what the posterior is when we have two unknowns. So what exactly would we like graph? Like what would we compare that graph to?
Yeah. What do you all think? So in situations like this, just look at the normal mu and sigma, both are very unknown. We actually don't know exactly what the posterior distribution would be, right? So whenever we're doing diagnostics, we should, like, is there anything that we should compare to when we're looking at the draws that we have?
Like the only, like, this is like just hazarding a guess, but like we learned last class that you can sort of conceptualize the two unknown parameter model as like two conditional one parameter models. So perhaps you could like take one of the one parameter models and like put it side by side with our approximation and see if there's like any similarity towards it. I'm not really sure though.
Yeah, so I would say that might not be a good way to do it, mostly because right now, say, whenever we need to use Gibbs samples, because both are unknown, right? What you were talking about earlier, like previously in the previous chapter, what we did is we assume one of them is known, we only work with one.
Yeah.
And then, so I don't think, so it's two different situations or setups. So I don't think it'll work. But to answer the question I asked earlier.
Oh, sorry, I had a question.
Oh yeah, go ahead.
So I mean, is a result like the weak law true? So like the samples sort of converge almost surely. Then in that case, if they get close to each other, then we know they converge because then their limit is unique. So.
So good. So I think that's another argument. And what I'm hoping to say is for the diagnostics that we're going to do now, typically it's only it usually just can tell us that it's not convergent. Okay, we're never be able to be guaranteed that it will be convergent, but some situations you will see soon that it's telling us it is not convergent. And then there are certain things that we can do, like the thinning that I talked about, get rid of the dependence between draws. And also like chop off the first, say, 50% of the draws that you start with, so you don't have the influence of the initial values, all that. So those are important things to do. But even if you do that, it's not guaranteed that it's going to be convergent. Okay, but if you run the chain long enough, make sure that you get rid of the initial values, their influence, and then maybe also like set aside adjacent draws, so you're only going to get independent draws as much as you can. Those will all be helpful. Okay, so with this in mind, let's look at a few things that we can check and then what we can do. So the first one is what we call Burnin, and you probably noticed that this is one of the arguments in the JAX code. Okay, the JAX script that we looked at, the round JAX function. So the reason here is that we don't want to have pre-convergence values to influence the summary, and that's mostly the first. We don't know the percentage. Typically, you do 50%, but sometimes you can do other percentages. So what we do is we're going to throw out the first 50% of draws as Burnin. So we burn them. We don't need them anymore. And we're going to only work with the remaining 100 minus p% of draws. Okay? So that would be a typical strategy to do. And in fact, if you're just gonna graph all of the draws, you might be able to see that at the beginning, maybe 50%, maybe 30%. Those draws are like far away from what it's being converging to. And then that will give you another idea of why, I think, the justification of why you want to convert it in the first place. Okay. But for simple models like the one that we're working with, I think it's going to be converging pretty quickly, in a sense that the first few, I don't know, maybe 10% is still exploring, but then soonish it's going to converge. Okay. But Burnin is a really good tool in this case. So that's what we do here. So the Burnin is this thing. So again, for JAX, there's also this adapt choice. I still don't know much about exactly what the adaptation is doing in terms of what JAX is trying to do. But typically, I just think of adapt and Burnin both as the draws that we're gonna discard. So you can use like 1,000 and 2,000 in this case, and then in the end, we are running 5,000 iterations towards the end, and we save those. And so you can think of any kind of combinations in terms of adapt and Burnin, but at the end of the day, only the number of iterations in the central argument going to be saved. Okay, you're only working with, in this case, the 5,000 that we have. I would say maybe just take the adapt and Burnin both together as the Burnin that we're doing, and then also indicate how many iterations you want to save in the end, and that goes to the sample argument. Okay. So that's discarding the initial values. Another thing to do is to check how well the MCMC is mixing, and we are able to use what we call trace plot. So it's showing the progress of the chain over time. So pretty much you're plotting the values of each parameter across the draws. Okay? And you're plotting it by time index, in a sense that by the index of the iteration. And if you see trace plot with a clear trend, say, like, keep going up, you don't really see it, like just keep going up, it doesn't like stabilize or something like that. That might be an indication saying that it has not converged. Okay, it's still exploring. And typical thing that you can do is to write it longer. Okay? And we also call something stickiness. And that would be the case where if you see a trace block, let me just give you a demonstration, that go up, and you can see that draws are very dependent from each other, right? And you see very little changes next to each other, but then all of a sudden you might have like a big change. And that's another indication of the chain is not converged. It's sticky in a sense that the adjacent draws are very close to each other. And then you might have a big jump or a drop at some point. But at the end of the day, you probably want to run it longer, and then together with the next technique we're going to cover, the tuning, you'll be able to see a better convergence. Okay. So again, it's hard. So all of the diagnostics that we're going to cover today, you should look at them all together. Just looking at one might not be helpful enough. Okay. All right, so let me give you some demonstration of what trace plot should look like. So in JAX, when you're doing this plot function of the posterior, so remember that's the object that we save, our posterior draws, and I want to just plot mu, then it's going to give you a diagnostics plot for 4 of them. Okay, and for now, the trace plot that we focus on is this one. So the 2x2 output from the plot function, the top left is the trace plot. Okay. And the trace plot, so it's hard to see from this because I need to like put everything in the same, so I have to adjust the figure a little bit. But if you actually run the markdown file, like the one that I shared, you will see it like better, I think more nicely looking, in a sense that you'll be able to see the up and down very clearly. This one right now, everything is sort of squeezed. But the general idea is that this is the case, or I would say an example of pretty adequately exploring the parameter space, in a sense that it's going up and down. So if you look at the actual plot, I think it's going to be something like this. Right? And this will be an example of a pretty adequate exploration of the parameter space in terms of the trace plot is mixing well. Okay, an example that I gave earlier will be too sticky sometimes, or too much rely on the initial values, things like that. And one more thing to notice when we're looking at those kind of plots is take a look at the iteration number here. So this is the demo that we did 1,000 adaptation, right? Adapt for 1,000, burning for 2,000, and then sample for 5,000. So you can see the iteration number here that the burn in and the adapt, they're going to be discarded, right? So what we're saving is really from the 3,001 iteration, starting from the sample, and it will go until 8,000. Right? So that's why you see the trace plot is only looking or plotting the ones that you finally save. Okay, so those are important to know. And it's important also just double check that you're writing your code correctly. Okay? So the iteration index here can help you to see that. Okay? So that's trace plot. And the third one is the ACF, autocorrelation function. So that again is trying to make sure that we can get rid of the dependency between draws, because we want independent draws in the end. Okay? So Monte Carlo draws are independent, as we know, so they're going to have 0 autocorrelations. MCMC draws, like Gibbs sampler, they're going to have non-zero, usually positive autocorrelations. So if you're going to have large autocorrelations, the chain would not mix well. It's going to be pretty sticky, like what we saw before, in a sense that if we see like things like this, right? So that indicates high autocorrelation, depending, like the next draw depends on the current draw, things like that. So when you look at trace plot like this, the autocorrelation plot will look bad as well. Okay, so that's why we mean that we should look at all of the diagnostics as a whole picture to see it. So if you have large autocorrelation like this one, it's not going to mix well. And it's very easy to arise in multi-parameter MCMC just because the parameters are highly correlated. So when you take the draws iteratively, you might end up with very highly correlated draws. So typically, if you see that, you should run the chains a little bit longer to feel more comfortable about the convergence. And we're also going to talk about effective sample size after I show you some examples of the plots. So all of those together will be able to help us to determine if we need to run the chain a little bit longer or not. So if we come back to this one, so again, I'm using the same script, and the autocorrelation plot is this one, bottom right. Okay, so this is the case. Okay, so lag stands for when you're looking at the lag of the iteration. Okay, so when the lag is 0, its correlation with yourself is always going to be 1, right? Lag 2, lag 1. Is like I'm looking at the correlation between the current draw and the next draw. Okay? And like 15, for example, will be I'm looking at the current draw and the 15 next. Like say, between me and the next, between me and the next one, there are 15 draws in between. Right? So when the lag is 0, it's always going to be 1. And this example, you can see that, well, the autocorrelation function drops pretty quickly, almost to 0. Immediately after 0, I would say. So this is actually telling us that the algorithm, if sampler is pretty efficient in this case, that we don't even need to do any kind of thinning, in a sense that the adjacent draw, even just next to each other, the autocorrelation is super low, like 0. Okay, but again, the model is simple enough to do it. But later, when we work with more complicated, more advanced models, you will see that. Well, you might see autocorrelation function like, let's see, so this is, let's say this is 0, this is 1, this is 5, this is 10, just as an example. So at 0, we always know that it's going to be 1, right? Autocorrelation. You're going to have something like this. Sometimes you might have autocorrelation like this, looks pretty bad. Okay, in a sense that the dependence between the draws is still very high, even if I go up to 10 or 5. So that later on, you will see that the autocorrelation function can give us good indicator in terms of how we're going to determine how many thinning we're going to do. So now we don't do anything, thin equals to 1, because the adjacent draw is very independent from the next draw. But if you have higher autocorrelation function, like the plot that we don't see now, but later, that will give you the indication that we should do a larger thing. Okay, like say every 10th draw or every 20th draw. So that's looking at autocorrelation. And one last thing that can help us is the effective sample size. Okay? And that's the alpha that I talked about earlier, that we're going to look at this one. So remember, the number of samples that we have is 5,000. Okay? And let me just tell you the definition of effective sample size, and I will ask you what do you think of these numbers here. So effective sample size of a MCMC is trying to evaluate, say, the sample is 5,000, right? And the column is going to tell you what's the equivalent number of Monte Carlo draws that we have compared to the current MCMC draw. Okay, so let me say that again. The MCMC draws we have is 5,000. And this effective sample size is trying to give you the equivalent Monte Carlo draws, meaning independent draws, that this 5,000 MCMC draws are equivalent to. Okay, so if that's what the effective sample size is evaluating, what do you think these two numbers are telling us? And do you think it makes sense? Yeah, let me add one more comment. Some of you probably noticed about this column. We typically don't look at it because, AC.10 represents the 10th leg of the autocorrelation. And so from the plot that we can already see a little bit, but together with this column AC10, we get 0.03 for mu and negative 0.002 for phi. Does that help us to understand the effective sample size that we have over here? I'll give you a couple more minutes to discuss. So what do you think? What do you think the 5,000 for mu represent? And we get an even larger than 5,000 effective sample size for phi, which is more than the number of draws of MCMC that we have. What do you think that is doing? Open-ended, so don't be shy. So what does 5,000 mean for the mu? That is slightly easier to think about. By definition, the effective sample size is representing the equivalent independent draws, the number of independent draws that we get, given this 5,000 MCMC. So for mu, we have 5,000 effective sample size. What does it mean based on the definition?
The draws are relatively independent.
Yeah, I guess super independent in this case. Yeah, even though you can see that we have a non-zero, slightly positive autocorrelation at lag 10. But overall, so again, effective sample size, I think it's approximation, the values that are giving. So this is together with the autocorrelation can give us a good sense of how independent those draws are. Okay? And you might be wondering, okay, why we get even greater than 5,000? I think it just depends on how the effective sample size is being computed. And specifically, I think whenever you're going to have a negative autocorrelation, they're going to count towards even more independent. Okay? It's just how it is being computed. So don't worry too much about it, but I just want to show you that JAX might not be doing the most perfect things out there as well. But what is important for us, I think, is to keep in mind that effective sample size, this column from the output, is actually pretty important. And I would say, as long as you see in like effective sample size for every parameter is like at least 1,000, I think that would be a good thing. Like, will be good enough to summarize. Yes, Jonathan.
So like if those numbers went to like 10,000 or something, would we see the autocorrelation like go to closer to 0, I guess?
Yeah, so it's hard to say. So good point. So running longer is one thing, and then getting independent draws is another.
Okay.
Right? So running longer, I think, doesn't mean that you're gonna get more independent draws. It's just you're running longer.
Okay.
But what it can help us when you run it longer, first of all, like you don't get, like say if it's not converged to like a space, you can run it longer. So you might go to that space. But when you run it longer, another thing it can help is that, well, if I know the autocorrelation is gonna be high, I will be able to do the thinning.
Okay.
In a sense that, well, I run it for 100,000, for example. And then I know the autocorrelation is really high. I'm only saving every other 100 draws. Then if I run it longer, I will be able to thin in that way that I can still get a good number of independent draws in the end. Yeah, so running longer I think helps. But running longer directly is not necessarily meaning that you're gonna have a lower autocorrelation. But it can help us to get to independent draws more easily. But running longer gonna take longer time.
Yeah.
So there's a trade-off. Yes, Aiden?
How come like the max value is not the same as the sample size? Like how does something contribute more than one?
Right, so
draw
that,
for
right, good. So I don't know exact the detail happening in terms of how Jack's computing it, but I think it's because of the fact that they're negative correlation, autocorrelation, and I think based on the way they're computing is sort of like actually added to even letting it more independent. I think it's based on the formula that they use. Yeah, but I mean, again, as we know, as long as you have non-zero, either positive or negative, they're autocorrelation, right? So so I don't know exactly for sure why, and but I think the JAX output that we typically see from this package does show you that. So it's good to keep in mind that it might not be the most accurate, but overall I think this particular column will give you a good, like overall a good sense of how independent those draws are. Together comparing to this, of course, as well as this column, as well as the ACF function plots that we saw earlier.
So is it like a sum of the autocorrelation?
Yeah, maybe. I actually don't know exactly. Yeah. So maybe that's what it is. But again, just like I don't know exactly what that adapt is doing in JAX. I think there's certain things. Yeah, again, people write those functions and they have to write how to compute particular things. So it might depend on how they're dealing with this. But I was trying to say that, well, if you have effective sample size for all of the parameters to be at least 1,000, I think it's a good time to stop that. You're going to just summarize the draws that you have. Okay, we want enough independent draws to summarize what we have, and then this will be a good indicator, like a rule of thumb. Okay. All right, so that's for the effective sample size. And so thinning, I've been talking about it, so now we can finally come to this point to talk about it. So thinning is this argument. So again, Monte Carlo samples come from independent parameter draws, and Markov chain create dependence. So what we do is you can use thin to save every x draws. Okay, so this x will just be the number that you put in here. So right now, remember, both mu and phi had really high effective sample size, right? Very low autocorrelation. So we don't need to do any kind of thinning. But if you see situations where you have really high autocorrelation, then you will increase this value to be 10 or 50 or even 100 or even larger, depends. And that will be able to help you to give the final independent draws. Okay? One thing to keep in mind is, I think is like something special about JAX is, so whenever you do sample, say 5,000, you're gonna have 5,000 draws in the end, okay? So when we do thinning equals to 1, that means they're gonna run for 5,000 iterations, okay? If you're gonna do thin equals to 5, what they do is they're gonna run 5 times 5,000. That number of iterations, but I'm going to only save every 5 draw. Okay, so that's why if you keep the same sample number here, but you increase the thin value, it's just going to take longer to run, and you will see it pretty quickly, because as you see the JAX output, they give you the progress bar, how long it's like how far it has run, and you can even like mark the time to see how long it's been running, how long you will take. So that's another thing. Good to keep in mind. Because one thing I should mention, like say, when I first started learning all of this, I didn't learn through JAX. I was coding everything. And what we do is say, if I realize, so I run a super long chain, right? And then what I do is you can plot the trace plot, or like plot the autocorrelation function, and you will see that it's pretty highly autocorrelated. So what you do is you just need to run a super long chain, and you have to do it by yourself by doing the thing. Like I have to write a separate function or like a loop, and then just do everything like I'm saving every 10th or every 20th draws like that. So that's another thing. To me, it's very interesting that JAX is doing this automatically, as long as you specify how many samples you want, and you can change the thing value. It's still going to give you the number of samples that you want. They're just going to factor the thing into it directly. Whereas if you're going to write your code yourself, just like the one that we did on Tuesday, the ones I share with you and then ask you to do the exercise, well, those are self-coded MCMC in a sense that I run it and I realize, okay, it's not long enough. I have to run again. I run even longer and then check all of the stuff that I need to do. Okay? So I think there's definitely flexibility of JAX. And as we get more familiar with all of the workings, I think you will feel more comfortable doing all of this in JAX instead of self-coding. All right, so again, we just come back to this. So this is the 4+ for mu. So mostly what we care about is the trace plot as well as autocorrelation plot. Okay. The other two, this one is the empirical CDF, and this one is just a histogram of the posterior draw. Okay. You can use them, but sometimes, especially now we use ggplot2, you might make it even nicer in your own way. So typically, whenever we're doing plot of the posterior itself and then look at the variable, I think we focus on this one and this one, okay, in terms of checking MCMC diagnostics. The other two are still useful, but we might want to create them separately for reporting the results. Okay. So this is the one for mu, and this is one for phi. Okay, so I think for both of them, as we know that the trace plot is mixing pretty well, and then the autocorrelation function is pretty low. So those are signs of it's mixing or like it's being converging. One last one I want to mention, we don't do much nowadays, I think, but still, another aspect of checking whether a Gibbs sample or MCMC chain is converging is that you run multiple chains. Especially you start at different values of the multiple chains and eventually check if they all come to the same point. Okay? So that I would say is probably the best way, or like the most correct way to think about it. It's just nowadays people do like say super long chain and then do the thinning and just hope that it's going to be convergent. But in the past, as you can see, when MCMC was first proposed in 1990, there are a lot of work following that. One thing is this Gellman-Rubin diagnostic. So what they do is run multiple M larger than one separate Markov chains, each of the same length. And then what they are checking is assume that the convergence is achieved for each of the chain. They're just going to look at how different, when it's converged for each chain, how those draws are. Okay? They want to compare. So if you know, not necessarily of course, but if you know about ANOVA in your other courses, you know that ANOVA is trying to look at across different groups, the within group variance and the between group variance. So Gellman-Rubin diagnostic is doing the same thing, except that they're not working with groups, they're working with chains. Okay? So what they do is they run multiple chains. Let me just, I don't know if this illustration will be useful enough. Let's say 3 chains. And I know, let's say, maybe I cut off the first 50%. I'm just looking at the within chain variance and the between chain variance, how different they are. So ANOVA is helping us to identify that, and the Gellman-Rubin diagnostics is like what we write over here, based on comparison of within chain and between chain variance. It's similar to ANOVA idea. Okay? So there are certain like threshold number that if Gellman-Rubin diagnostics is being computed, you should pass that in order to make sure that you are indeed passing this diagnostic. So this this part is still interesting. I think it's important to cover. So just now when we run the JAX, I don't think we initialize any values, right? We just let it run. So it's just going to JAX going to pick a random number to start. But you can't force specific initial values in this way. So what you do is you create this init. In this case, because we're trying to do 2 chains for the gamma Rubin diagnostic, so we do 2 of them. And you'll see that I'm setting mu equals to 1, phi equals to 1 to one of the chain, and mu equals to 10, phi equals to 10 to the other chain. Okay, I'm forcing those starting values for JAX to take, and then let it run in this way. Okay? So this is still good to know, I think good to use later if you do want to give specific starting values. And then once you do that, just see the change over here. We add one more argument of this init. And we put the inits 1 and inits 2. Okay. And also don't forget to specify the number of chain to be 2 now. Okay, so JAX know that, okay, I'm going to run my first chain with those initial values 1, 1, and my second chain with 10, 10. Okay. I'm still not doing any cleaning or anything, and I keep everything the same. I save the same parameters as before. Okay. So the good thing is now, so I save things in this posterior underscore 2 chains, because later I will be able to extract draws from it. So one output is the gamma Rubin diagnostics. So I think this is the output, and I think anything smaller than 2 will be a, I think, I have to double check actually, will be showing that it's passing it. And more importantly, let me show you this one here, that now if you're going to plot the posterior underscore 2 chains and then looking at the parameters of mu, because now we have 2 chains, they're just going to color code it for you directly. Okay, and it's specifically, I think, evident in the trace plot, because now you can see 2 going on. Okay. So this is another, I guess, demonstration of how well the mixing is doing, because the 2 are really similar, but they're still exploring like similar region, but they start at different values. So at some point, so in this case, starting from the 3001 iteration, you can see how well they're exploring the space. So that, again, I think running multiple chains to make sure that it's convergent is also a good practice to do. All right, so lastly, so what I talked about so far is doing MCMC diagnostics with JAX, right? But if you write your own code, you can use this CODA package that have a lot of functions there to help you do those diagnostics if you have your own MCMC, okay? So JAX, the one that we see so far, like plot, you can see those plots. But trace plot itself as a function, if you have your own MCMC object, you can use this to plot it, okay? And autocorrelation, so autocorr.plot, giving the autocorrelation function. The effective size is getting the effective sample size, and that's the name of the function. And lastly, the gamma Rubin diagnostic that we talked about, you'll be able to get it from this command. So I don't think I include, like, say, output of how to do this, but at least I think what we did before is we wrote that Gibbs normal function, right? And then you get the input into it, the number of iterations, and you set the seed. So that's what we did last time. And we save it into this para post with column names, mu and phi, so we're able to extract it later. So the only new thing here is that make sure that you download, install, and then load the CODA package. Okay, so this package contains all of the MCMC diagnostics function that we covered. So down here, this is how you can use those functions. Can you use this as MCMC, a function to put your draws into an MCMC object, which is a requirement for the CODA package. And then you just use this as the input to all of the functions that we just covered. So this is, I guess, handy in the future, maybe not so much in our course, but in the future, if you ever run into models that JAX might not be able to do it for you, and you will have to write your own MCMC, maybe Gibbs sampler, maybe some other algorithms, the CODA package will be super helpful to do the diagnostics that you need to do. But for what we focus in this course, I think JAX will be helping us doing the actual sampling, as well as all of the diagnostics that we've been talking about. Okay, so that's sufficient for sure. But I thought this would just be useful for the long term. All right, I think that's all I have for the diagnostics. And what I would do, I think we have a few minutes left.